Especially in the last 2 years, a recurring interest in our program has been in how design uses models and how models in turn design what it is that they model. And this recursion is most explicit, perhaps, with complex computational simulations. Financial markets, for example, are themselves intricate simulations of what flows of value are most likely, and hence the real economy we saw in the vault becomes a model of itself. But as Donald Mackenzie puts it, financial markets are really more an engine than a camera. They help generate what they describe by setting the terms of what is and is not a calculable risk. Today, more broadly, these simulations are used to train AIs in how to do things in the real world by having them first master the virtual ones. And as you'll see, large companies maintain, for example, digital twins of their complex machines, such as jet engines, that mirror the real-time performance of the original. Now, that's okay but what if a simulated problem space, like a city, needs to be modeled by many different actors at once, none of which can know everything that they need to know about all the variables, but all of which of these actors need to know answers that depend on what the others know? What if the division of cognition between these actors, some governments, some companies, some scientists, isn't really the ideal way of dividing up the problem and ends up causing more confusion? Our next project, Sybl, suggests one possible answer: less an AI gym than a kind of open stadium for multivariable simulations to interact with one another. It would make computational simulations more open, available, and powerful way of knowing and designing. Lastly, this project may, at first glance, seem quite technical compared to the last, but is also, in the best possible sense, perhaps the most utopian of the projects that you'll see today. So, my pleasure to welcome Sybl.
Hello, my name is Ricardo. I'm a designer from Brazil.
Hello, I'm Grigory. I'm a computer vision engineer from Moscow.
Hi, my name is Maria-Veronika. I'm an architect and artist from Moscow.
Hi, my name is Mark Wilcox. I'm a software strategist from New Zealand. And we're going to play a video, introduce you to a software concept called Sybl, and it's an open platform for enabling simulations across domains.
High-performance computing is the engine enabling almost all modern science, technology, and consumer product breakthroughs. Simulations enable us to extend beyond our basic working memory, to design and build systems whose complexity would be otherwise unfathomable. Today, simulations are trusted as digital twins to directly manage the operation of complex mechanical systems. A digital twin is a virtual representation of the elements and dynamics of an IoT device and the environment around it. A twin becomes intelligent, not just by capturing the data, but by processing it through powerful algorithms that learn and grow in tandem with the physical entity. Our dependence on computer modeling only increases as real-time data demands reach new heights with 5G data networks. So the esoteric language of scientific computing needs to be transformed and needs to come out of university basements, government agencies, and corporate R&D labs into global networks, where we can observe, evolve, and govern them in the future. Despite major advances in digital modeling, render engines, and AI methods, the current architecture of simulations isn't able to incorporate the dynamics of an increasingly complex world. The limitations lie both in the lack of common formats that support the integration of simulation modules across different platforms, as well as the computing power necessary for large-scale simulations with overlapping domains. There exists a virtuous cycle in AI research in which the development of novel environments can enable the development of novel algorithms and vice versa. This effect can be seen in how games and AI have been intertwined. In a similar way, the ability of researchers to create complex environments that mimic the conditions found in the real world can lead to physical spaces through which new simulation techniques can emerge. By applying the same thought process to simulation spaces, we can begin to build a picture of a meta-modeling environment, where engines and algorithms can be combined, multiplied, and averaged. The use of game engines as simulation platforms for autonomous vehicles points to the necessity of a networked platform that is able to support the instantiation of complex systems with real-time data, such as traffic and pedestrian activity in the city. Game engines offer a high level of modularity, but their architecture can't scale to the growing demand for complex simulations because of their core role as a general simulation environment that only runs on one computer. The creation of an open simulation platform could rapidly increase the potential that simulations could play in the near future. These environments need to be much more sophisticated than what you would build in a game. They need to be able to ingest the real-time data for entire supply chains and ecosystems at ever-decreasing timescales. Sybl is a collaborative and modular programming environment that connects previously isolated computational models in one simulation space. Sybl extends popular programming and simulation engines by introducing a modular ecosystem where simulation models can be combined, increasing their resolution, accuracy, and dynamic complexity. Designed around an intermediate format, Sybl displays commonalities between packages, establishing a link between different engines, and augmenting the standalone software architecture paradigm. This enables real-time investigation of events within a simulation, while also producing high-precision datasets for downstream applications, such as machine learning and computer vision. By introducing an open format, the platform links data markets across different disciplines, with simulation tools and engines already available on the market. As different applications are chained together, changes are registered into a common reference model, converging into the same simulation space. Sybl is designed to simplify the modeling of complex systems, facilitate the integration of different simulation engines, and enable interactions across different scales and domains. Simulations are run in an open environment, enabling different experts across organizations to work together in real time. This means that simulations can achieve higher complexity without sacrificing resolution in any one application. Sybl introduces universal visual programming, bridging existing modeling and rendering packages across disciplines, making it easier for experts to work together. Simulations in Sybl operate within overlapping address spaces, which enable them to interact with each other, sharing data and adjusting their predictive models. Sybl's real-time data markets allow for the sharing and licensing of models, datasets, real-time feeds, and visualizations. From the car companies to urban designers, insurance agents, and traffic engineers, simulations enable different actors to better understand how different policies might change the urban landscape. While achieving a high level of resolution within themselves, these simulations remain largely isolated from each other. Sybl's real-time open market enables multiple organizations to run their models in the 5G infrastructure, allowing them to interact while keeping control over individual parts. The result is an emergent multi-stakeholder modeling environment that better captures the complexity present in real-world systems. In this new simulated space, policies, urban infrastructure, software and hardware development become linked by their common interdependencies, being able to react to changing demands. Sybl becomes a meta-modeling application able to monitor a recursion between simulations on different scales. The platform makes it possible to build reconstructed models of events that happened in the past, tracing their interconnecting dynamics across timescales, providing data for analytics and future prediction. For instance, Sybl makes possible a multi-scale modeling of epidemiology, plugging together simulations of contagious transmission from molecular level through the human body and into the city, tracing how the disease can be spread via air travel. Such approach helps to reveal feedback loops between simulations and unlocks recursion between scales. How the molecular level impacts the city, and how the city level reflects back in the molecular. When the control and reasoning over the functioning of infrastructure moves to a simulation environment, the distinction between the physical and virtual changes to a new configuration. One that prioritizes the digital as a constant object, while the physical is in a perpetual state of update and optimization. By creating a space for the integration of digital twins of complex real-world systems, their digital models can begin to co-evolve, reshaping how they're conceived. In this model, a digital twin is able to integrate and optimize for interactions, actors, and environments that run beyond its scale and domain. As powerful a tool as computer modeling is, it's no replacement for the real world. We need to constantly reconcile our models with reality, or our models will redefine us.